So up until this week, we've been mostly focusing on vector data. We're going to start focusing on rasters though. Rasters are a fundamentally different type of data. Remember that vectors are points, polylines, and polygons. There's also tins, but we don't work a lot with those until you get into more advanced hydrology. Rasters are different. Specifically, they cover an area with a grid of cells or picture elements, pixels. That's an important term to remember. Picture elements means pixels. And they cover it evenly. So here we've got a digital elevation model of Mount St. Helens. We've got one before and one right after the eruption. Pretty cool data set. And here you can see the high values are at the peak of Mount St. Helens, and then they go down as we go down in elevation. Same thing here, except the caldera blew out and blew out to the north. We can see that here in this 3D hill shaded image. Pretty cool stuff. And now the high values are around the ridge that's remaining and then going down to low values. So rasters are really important in natural resource GIS. There's a lot of different things you'll find in them. Just a few is elevation, depth, or bathymetry for water depth, temperature, precipitation, habitat suitability, landslide risk, slope, aspect, all kinds of things are done in rasters. And it's important to know that we also convert back and forth between raster and vector as you just did in the watershed lab. And there's a time to do that based on what type of analysis we're doing. Rasters also add a bunch of new analysis methods, raster math, which we'll play with, topography or terrain analysis, reclass, raster to vector conversion, statistics on rasters, histogram analysis, and then raster data representation and visualization. We'll touch on all these in the coming weeks. Before we get started, a few things to really keep an eye on when you're dealing with rasters is keep the size below 200 megabytes with ArcGIS. If you're in a remote sensing product, if you're in Blue Spray, you can go above that. But ArcGIS tends to crash the bigger the rasters get, tends to slow down. Also, I should have put on here, don't access them off of a cloud-based drive. Every semester, a few students start crashing Arc, or it takes forever to run raster data, and I find out they've been running off a cloud drive. Copy it down to your desktop, as we talked about early in the semester, and then bring it back to Google when you're done, or cloud drive, and then bring it back to your desktop to work on it again. You've got to get used to doing that, or Esri will crash. Resample is the tool in ArcGIS to convert rasters to smaller ones. In other words, to downsize them or decrease the resolution. So if you've got a 1 meter LiDAR DEM and you don't need that, you want to get it to 10 meter, you can resample it to 10 meters. Crop and Blue Spray works really well and really fast on large rasters. You have to be able to load them into Blue Spray, but once you can, it's really fast and easy. If it's bigger than it'll fit in Blue Spray, you're going to need to go to remote sensing data or try it in Arc, but a lot of times it'll just crash on big rasters or never finish. And for that, keep an eye on results and geoprocessing. Okay, sometimes errors will just pop up and then they disappear, and so Arc's sitting there and you don't know it, and you're waiting sometimes for hours when in fact it's just already crashed. It'll probably crash up and lock up on you completely at some time in the next few weeks. When it does, fire up the Windows Task Manager and just kill ArcGIS. And then go fire it up again and try again and keep going, or try on a smaller raster. That's a really good thing to do. Go to a smaller raster when things are going badly, get it working a smaller one, and then see if you can increase the size. And by size, we mean either the resolution or the extent. Okay, there's ArcMap, a little bit of review here that I will do in another video for ArcGIS Pro. And what we really want to talk about is the data model. So here you've got a DEM, which is one you've been working with. We're working with part of it for Arcata Forest, which is right in here. Okay, and there's Humboldt County. And the important part is when you zoom in, you start to see more detail. If you zoom in again, you'll start to see squares appear. And if we zoom all the way in, way in, you'll start to see that not only are there squares here, which are our pixel elements, so this would be one picture element or pixel, but there's numbers there. And you can display these in Blue Spray with one of the painters in Blue Spray. And you can see these are just numbers. And that's really what's in a raster. It's just numbers. It's not shades of gray. That's the computer making it look like shades of gray so that we don't have to look at these numbers all the time, but we can look at it this way. And those are arranged in columns and rows, just like a spreadsheet. So a lot of ways, rasters are more like a table in Excel than anything else. And this is true of DEMs. It's also true of the photographs you take with your camera or cell phone. All right, a little bit of a review on data types. We touched on this with attributes, and these are the ones we tend to focus on attributes. We're not talking about text or dates yet. They're separate. Can't put text or dates into a raster. It has to be numeric values. So we've talked about using long integer because it's 64 bits. You rarely need anything bigger than that, and if you do, the computer doesn't support it. Floating point, we use 32 bits, or by default, I tend to use 64 bits because, again, it's the biggest number of bits. That means we can do these huge numbers, and we basically don't have to worry about running out of numbers to represent. Now, with rasters, a lot of times you will see things like unsigned byte rasters. In fact, your color photographs you take with your camera and upload onto a social media site are 8 bits. In other words, they can only have 0 to 255 as their values in each pixel. Now that's a problem because a lot of the data we want to represent, 0 to 255 is just not enough. Okay, you'll also see unsigned short for DEMS because it goes from 0 to 65,535, and I believe Everest is 27,000 feet. So that's the biggest value we'll ever see on the planet. Well, that's fine until you start doing mathematics. And notice we've got no fraction here. We need to have a fraction. So with rasters, we will mostly be working with 32-bit floats. We won't be working with doubles because Esri doesn't support it, although some remote sensing packages in Blue Spray do. Okay, and these are the values that are supported for the Esri rasters. Okay, so signed integers or 32-bit integer. We don't have a 64-bit integer, and then a float raster or floating point 32-bit. Now notice the names are a little different. Esri is not consistent in their naming. So depending upon whether you're talking about attributes or rasters or a geodatabase, the names are going to vary a little bit. Okay, but these are the two we'll focus on for rasters. Signed 32-bit for integer. And again, we don't see that very often. Once in a while, we normally like to work with floating point 32-bit so we have that fractional value, especially with any kind of math that we're doing. All right, so here's properties dialog. This is the one for ArcMap. I'll show you the one for ArcGIS Pro in a different video. So here's some common data types. Again, you'll see different values. If you're working with these and doing any types of arithmetic, again, the thing you want to do is convert them from integer to floating point and do all your arithmetic in floating point. Now, mostly we've talked about one-band rasters, but you can have multi-band rasters. In other words, to represent color like this, there's actually 3 different colors, red, green, and blue. We'll talk about that. You can also have measurement codes. NLCD is a really common one, but there's other ones as well. So normally we'll have like precipitation. These are just numbers. But if we go over to ground cover types, suddenly there's integer values, and these integer values represent different types of cover on the ground. So they're codes. So here you go, each code, each value in the raster means something different, okay? And you will work with those with NLCD in the future. Okay, so this idea of pixels, if we go here and move our cursor around, you will see the actual pixel values in this image. Okay, if we go over here, you'll see it's 0 because that's elevation of 0. Now this one looks like it's been scaled. I'm not sure which units it's in. Okay, oh, it's an 8-bit image because it's displayed on the web. So that's why it goes from 0 to 255. So this is just for demonstration. Okay, but note that there's just numbers underneath these pixels. Now similarly, if we look at this little aerial photograph of Humboldt, you'll see there's values there. Now, these are red, green, blue values. So notice if we go over here, red, the first value, 234, is bigger than the other values. But green and blue still have some value there. It's really rare to see a real solid red that's 25500. It's just not naturally seen from aerial photography. Let's see if we get a little bit better red here. Nope. If we go here, we'll get white, 255, 255, 255, or it's blown out. There's our 0 to 255. Here's one that's mostly blue. Here's some greens, where the greens are higher. But again, you'll see it's difficult to get it to be 0 to 55. 0, normally the color that we see will just be higher than the surrounding colors. Okay? But important to note, red, green, and blue, RGB, 3 different values in each pixel. Okay. We're going to find that a little more formally. There's 4 different types of resolution associated with each raster. The first one is spatial, and this is by far the most important. So here we have 1 meter resolution aerial photography, then 10, then 30. And if we look at this from a remote sensing standpoint, if we're trying to do any analysis, like, well, why wouldn't we just use the 1 meter all the time? And it used to be that we didn't have 1 meter resolution available. We only had 30 meter Landsat for the entire planet. Well, we're getting more and more 1 meter res. We're getting below 1 meter resolution. Incredible data from UAVs. Why wouldn't we just use that all the time? Well, the problem is it's huge data. Okay, in fact, as you go from 1 meter resolution to 10 meter resolution, and this is really important to know, the size of your files, or the number of pixels in your file, goes up by a factor of 100. Because it goes from 1 meter resolution to 10 meter resolution in the X, Okay, so this is really important to remember, is that as you go from 1 meter resolution to 10 meter resolution, in other words, as you go from, these very detailed pixels and you drop to 1/10 the resolution, okay? Instead of 1 meter per pixel, you get 10 meters per pixel, or 1 pixel every 10 meters, okay, in this one, versus 1 pixel every 10 meters. Your resolution is dropping by a factor of 10, but it's doing it in both directions, in the X and the Y. So the number of pixels in your raster is dropping by a factor of 100. That's really important to know, because what that means is the opposite is also true. As you go from 10 meter to 1 meter, the size of your files is going to go up by a factor of 100, and everything's going to become really slow. Same thing with 30 meter. Landsat, yeah, it's 30 meter. It's not very good resolution, but we can cover the whole world with it. You can do very large extent research with it. But as you go from 30 to 1, the size of your files is going up by 30 times 30, or 900, 1,000 times bigger. So you want to be careful with that. There's a little summary of that. Okay, the next one is spectral resolution. We already looked at Mount St. Helens before and after. Sorry, here's the before or after one. Notice it only has 1 band. Okay, that's the spectral resolution, is the number of bands. So you only see grayscale, that's it. The 3-band image that we have for HSU, well, it's 3 bands for red, green, and blue. Some of you will get into remote sensing. You'll learn about hyperspectral, lots of different bands. You can detect infrared, which is really important, natural resources, but also radio waves and all kinds of things. So there can be more spectral resolution. Temporal data, there's Mount St. Helens before and after. Depending upon when you collect your remote sense data, because most of our raster data is based off remote sensing, the planet's changing. It's changing all the time. And that's something we have to take into account, especially when we're doing analysis, because each raster is something captured in time, in that moment in time. And the world keeps changing and the raster doesn't. Finally, and probably the least important, is the radiometric one. And this is the depth. This is, again, our bit depth. Usually the red, green, blue images we get, or the satellite photographs that look like digital photos, are 0 to 255, or 8-bit for each of the red, green, and blue bands. However, you can get 16-bit remote sensing, and then we do analysis. We like to keep it at 32-bit float. So that's the radiometric resolution. We put all these together, we've got a model where we have to think about all these different resolutions. Now, we really don't think a lot about radiometric. We think about the data type. We think a lot about the spatial resolution, because that's our data size. And then the spectral resolution is, again, how many bands. We'll play with those with Landsat, and it depends on the type of work you're doing. Temporal is also important, but we tend to forget about it once in a while. We need to not do that.